All right, hello and welcome back. Today we're going to start a new chapter or collection of chapters in 8A, and I'm gonna go about it perhaps in a different order than what's being done in lecture, but bear with me because there's a method to the madness. We moved through physics a certain way at the very beginning, and we started with forces and F net equals 0, and then we said, oh well, F net could be also ma if there's motion, accelerated motion anyway, and then we talked about work and energy, and we moved in that sequence because it made sense. It made sense to first understand forces, understand what it means for F net to be 0, and then what it means for F net to be ma, and then think of things in terms of energy, kinetic energy, potential energy, and things of that nature. And for whatever reason, in most cases, the torque chapter is taught, in my opinion, backwards. We don't start with just defining torque and torque net equals 0. We actually do that last. We, more often than not, start with torque net equals I alpha, or perhaps even with rolling without slipping, and then do everything in the reversed order. So that never made sense to me. I think the biggest issue with torque is that there's a lot. You could think of it as 3 separate parts or 3 separate chapters, just like we had, 3 separate chapters for the previous stuff, kind of. And there's a lot of material, and the excuse that you're always given is that, oh, well, you've done this before, it's the same thing, so just imagine that it's the same thing, and boom, we're gonna, in 2-3 lectures, we're gonna fly through this stuff, and then we'll be doing fluids before you know it, and you won't have any idea how to deal with torque. So torque is not straightforward. Torque is a different way of thinking about things because it's, it's associated with different type of motion or absence of motion. And I'm going to go about it the same way we went about the previous stuff. So we're going to start today simply with what's called statics. That is, we are going to quickly review torque, and then we're going to work on problems that involve static equilibrium. And we're just going to get good at writing torque net equals 0 along with F net equals 0, which we already know how to do. And that's it. And then from there, we'll move on next week to torque net equals I alpha, tie in kinematics, and then we'll move on to energy, rolling without slipping, things of that nature. And the goal is to really just chop it up so that it's, bite-sized pieces in a sense, and there's actually time before midterm 2 to do that. And if I ever realize that we're short on time, I'll fit an extra live stream in to cover fluids to the extent that fluids are even on midterm 2, which they might not be. So the point is there's time to do this, and from experience, I'm pretty convinced that it's the right way to do it because, again, torque is not intuitive, and there's a lot of things that we gloss over if we kind of speed through it, and the excuse of, oh, it's the same as forces, you've done this before, I don't find that to be a good excuse. I think that's kind of dodging the difficulty and going a little too quickly through the material. So today is just going to be torque. We're going to go over the definition again, and then we're going to work on problems that involve equilibrium. And if you're new here, this is a weekly live stream. You can go to slackademia.com and enroll in the free course that is the Physics 8A live stream course if you want to find these live streams, the practice problems that I do, as well as the homework solutions all in one place, and it's free. And of course, you can reach out through the website or through our Facebook page. So before we get into torque, let's point something out, okay? Something that that has been our assumption all along. Our assumption all along, up until this point excluded, has been that objects, yes, have a shape and size, but no, it does not matter. And so whether it was a car, whether it was a crate on an incline, whether it was an elephant or, an ant, it didn't matter. We just said, you know what, forget the shape and size, irrelevant, shrink it to a point, right, which is a mathematical point with a mass m. And this point, because it's a mathematical point, it's not a little marble. It has no top, no bottom, no front, no back. It has no dimension, right? It's a mathematical point. And so when, we have, let's say, a crate of mass m on an incline, well, we just draw it as a point. And as a consequence, if we were to draw the free body diagram of this thing, let's say it's at rest on this incline, we would just draw all the forces acting on the same point. The normal force, there's got to be static friction if it's at rest, and then there's mg, the weight force. Okay? But we had a point mass, so all the forces were applied to the point. In other words, it didn't matter where the forces were applied. Okay, well, today we're going to talk about extended bodies, which basically are objects that, well, have a shape and a size, and it matters. Okay, a ladder, for instance, you can't just say a ladder, oh, it's a point mass, I'm going to shrink it to a point. That's absurd. The whole point of the ladder is that it's an extended body. That's why it reaches, to the roof if you want to get onto the roof of your house or something. So we can't just go through life saying everything's a point mass. And we have to at some point acknowledge that there are objects that are extended bodies, and the way they behave or move or don't move has to do with their shape. And so a good example would be to say, well, let's take a very simple example. You could take a piece of wood. You can think of a wooden ruler, perhaps. And let's say you drill a nail through the center onto a table, let's say, a workbench or something like that. Okay. Well, it turns out where you apply the force, let's say you want to apply a force F1 on this thing. Well, where you apply the force actually matters, because if you apply it here, and that's the only force, because it's free to pivot around its center because it's nailed through the center, well, I suppose not actually nailed so that it's not free to move, but okay, there's an axle, a little axis of rotation in the center, and it's free to rotate about its center. Then if you put the force F1 there, it's going to go clockwise. But of course, if you put the force F1 here, then, well, guess what? It's going to go counterclockwise. So it matters where forces are applied when it comes to an extended body. Okay, so all an extended body is an actual object that has a shape and a size that matter. We don't neglect them. And it affects how the object moves or doesn't move. Okay, so here the shape and the size matter. And that's because where you apply the force actually matters. Okay, so it's not the same thing to apply F1 on the left end or the right end. Okay. Now, that leads to a new type of motion, because if you think about what happens if this can rotate about its center, well, it will. If you apply F1 on the right-hand side like that and it's free to rotate, it's going to go counterclockwise. Now, that's not a type of motion that we've ever seen before. Now, you could say, well, isn't it circular motion? It's like, well, I mean, sure, if you put a little sticker here on the, let's put a pink sticker on our little ruler there, then for the pink sticker, yes, it's true. If you just follow it, you'll find that it moves along a circular path. And you could argue that just for that sticker, it is circular motion after all. And that's pretty true, fair enough. But the thing is, when you're doing that, well, you're not accounting for the entire body. You can't just say, oh, I'll just look at one slice of it. No, you have to look at the whole thing. Okay, so what the whole thing does is actually rotate, and rotation is a very different type of motion than what we've studied so far. So we need to acknowledge that there's this new type of motion, and in so doing, we come up with a problem. What's the problem? Well, let's consider this ruler again. All right. Let's now have F2 pointing downward on the left hand there. And let's make it so that in magnitude F1 is equal to F2. Okay? Well, if I do that, then F net y is going to be 0. It's F1 minus F2 is equal to 0. So that means no linear motion, right? I can't get this. I can't get this thing moves up or down because F1 is equal to F2. However, even though the net force is 0 and we start at rest, we're not in equilibrium because this thing, if you apply these two forces, has no choice. It has to rotate counterclockwise. So in other words, the equations that we have are good at describing linear motion, and we never pretended otherwise. Okay, F net x equals 0 if you're at rest means you don't move left or right. F net y equals 0 if you're at rest means you don't move up or down. Fair enough. So that takes care of that, but clearly F net y equals 0 only prevents me from moving up or down. It does not prevent me from rotating counterclockwise in this case. So I'm lacking equations that will describe this new type of motion, which is rotational motion. And I mean, to be expected. We never accounted for it before, we never worried about it, and so we never really took the time to describe what might or might not cause rotational motion. And so that's where torque steps in. So again, our goal today is to understand, first of all, that we're going to be looking at problems very differently. Okay, we're going to go from a point mass with a free body diagram that looks like this to what's called an extended body, where we actually call this an extended free body diagram. You draw the entire object, and where you apply the forces matters. And their direction, of course, matters too, but where you apply them is something that matters a lot because it dictates what happens or doesn't happen when it comes to the rotation of the object. So again, that's the goal of today, is to acknowledge that and to say, okay, well, how do I describe the fact that this thing might rotate and that a force, even though it cannot create vertical motion here because F net is 0, still creates rotational motion. Okay, and that is what torque is. Torque is a measure of how much rotation a force causes about what's called an axis of rotation, or sometimes we just say pivot point, which is a bit of a simplification, but works really well because we only consider two-dimensional motion, right? In other words, rotation in a plane. We don't do Olympic, what's it called, diving, right? Where you have rotation in 3 dimensions. Okay, so it twirls one way and it rotates the other. We don't do that. So we only do things like this ruler on the table. It can only rotate in this case, a horizontal plane. Or the Ferris wheel can only rotate in the vertical plane. Okay, but we don't do a Ferris wheel that rotates and also wobbles in and out like this. That's too much going on. We don't do that. So let's talk about torque, and then let's see how we can apply the equilibrium condition. Okay, so torque created by a force. Okay, let's just remind ourselves of the definition because that's always helpful. Torque is the measure I should say a measure. Torque is a measure of the amount of rotation created by a force about an axis of rotation, sometimes also called a pivot point. Okay, so let's say this is a door,
viewed from above. It's a simplified door, okay? But it's hinged with an axis of rotation here.
And I'm looking at it from above.
Okay, now if you were to draw the door in perspective, like this is your door, then you would put here what we call the axis of rotation. This is your axis of rotation. The door will swing about that axis in one direction or the other. And it is the proper term, and really we should call it an axis of rotation, but the truth of the matter is that if all we do is look at it from above, and all we see is this, then we tend to call this, rather than an axis of rotation, simply a pivot point. Right? If I only have this 2D motion viewed from above, then really it's like a point about which the door pivots, even though, of course, mechanically that's not really what's going on in 3 dimensions. Okay, you have an axis and not just a point. But because we only do plane rotational motion, so rotational motion that occurs in a plane, either the vertical plane, like the Ferris wheel, or the horizontal plane, like the ruler on the table, well, pivot point's good enough. That gets the idea across. Okay. Now, let's still imagine that this is the door viewed from above. Let's say that we apply a force, F, like this, on the door. And let's perhaps say that we know the direction that F makes with respect to this dotted line, and that this is an angle theta. Okay. Well, you might intuitively know, or at least from experience anyway, if you've ever tried to open a door, particularly a heavy one, then of course it's a lot easier to push on the side opposite the hinges than right here. It's going to be a lot harder to open the door by pushing here than by pushing here. That's because, again, where you apply the force matters. The further away you are from your pivot point, the more torque you're going to get because of distance. And so it means that we need to know what this distance is. Now this distance, oh come on, there we go. This distance is typically called little r. It is the distance between the pivot point and the point where the force is applied. So I should make sure that I draw my force here. Okay, that's the distance r. Okay? And if I want to figure out how much rotation I get out of this force, that is going to be the torque created by the force. Now, the door could go either way. Right? It could go this way, which it does if I exert a force like this. But if I exerted a force this way, then the door would go clockwise. So it's a new type of motion, and there's no left or right or up or down really. It's counterclockwise or clockwise. Okay, but the same idea. The same way we say to the right is typically positive and up is typically positive, we tend to side with counterclockwise being the positive direction for rotation. In other words, a torque that causes or tries to cause a counterclockwise rotation is going to count positive. Now, you could flip it all around. You could make clockwise positive if you want. I might do that from time to time. But overwhelmingly, the default is counterclockwise is positive, comes from math. Okay. So the formula for the torque, I'll just write it. I'm going to write it here. I'm going to try to fit everything on one screen. So the torque due to F is going to be equal to, I'm going to write plus or minus, even though in this case it is positive because it tends to try to rotate the door counterclockwise. It's plus or minus r, the distance, F, sine of the angle between r and F. And that's the angle theta here. Okay. Now you can think of this formula as 3 separate terms that you multiply. That's fine. Or you can think of it as the following. You can think of it as r times what I'm going to call F perpendicular. Now what's F perpendicular? Well, F sine theta is F perpendicular. F sine theta is this component of the force. Right? hopefully by now that's no surprise. Okay, so this is F sine theta. Okay, and I know, by the way, that I can take vectors and I can slide them around. As long as I don't change the length or the orientation, that's fine. Okay, so this component would be this guy here. Okay, so this is why we call f sine theta f perpendicular. It's the component of f
that is perpendicular to the door. It is, for that matter, the only component that is important, because
even if you wanted to argue that this is f cosine theta, and we should call this f parallel, which fine, it's
parallel to the door. Well, f parallel does nothing in terms of opening the door. You could grab a door like that, right? You could grab it, both handles in your hand, and try to pull toward you. Well, that's not going to swing it left or right, now is it? The component that's going to swing it left or right is this guy. So that's the important component. So you could either say, well, look, it's just going to be this distance times the force times sine of theta. Fair enough. It's the same thing as saying it's this distance times the perpendicular component, which in and of itself is f sine theta. Okay. So I bring that up because it's important to realize that only perpendicular components to the door, when it comes to force here, will create a torque. The torque created by this is zero. It doesn't create anything. It doesn't swing the door left or right. Now, that's one way to look at it. It's perhaps the most common way to look at it. Either to say, look, it's just RF sine theta. I'm not even going to think about it. I'm just going to multiply RF and sine theta. And then in some cases, it's convenient to think in terms of components and to introduce F perpendicular. There's another way to look at it. Now, this one is not as common, but now and then it's the only way to solve problems. Depending on how the problem is written, it might be a very good way to solve. So let me get rid of these components because I don't want to think about components anymore. I want to say, okay, well, look, we said torque due to F is going to be plus or minus RF sine theta. Okay? Except now what I'm going to do is I'm going to pair the sine theta with R. So you could call it R sine theta F. Of course, makes no difference. Okay, but R sine theta is what we're going to call R perpendicular. Okay, and R perpendicular has a name. It's called the moment arm. And then what the moment arm is the only distance that truly matters when it comes to rotation. Okay, it turns out R is not really what matters. What matters is this distance here. So if I do this, if I draw this line here, you could draw it on either side of F. I don't really need it on the right side here, but I'll draw it just to be clear. This line is called the line of force. Okay, it's the line along which the force F lies. Well, the only distance that really matters when it comes to rotation is not R. It is, in fact, this distance. Right? It is the mathematical distance between the pivot point and the line of force. And it turns out that if this here is theta, then so too is this. And this is R sine theta. R perpendicular here is R sine theta. So you can think of torque in two ways. I would say the most common way is this, okay? But occasionally you'll find problems where you don't have R, you don't have theta, and therefore it appears as if you're not able to compute the torque due to this force, except you could remember that maybe you don't know R and maybe you don't know theta, but maybe you know this distance, which is R sine theta combined. All right. So those are the two ways of thinking about torque. And so torque is just a measure of how much rotation you get from a certain force
with respect to a certain pivot point. Okay, because what I wrote here is applicable as long as this is my pivot point. If my pivot point is different, then, well, that'll change the torque, because I typically want to compute torque about my pivot, and perhaps that changes R, maybe it changes theta to be determined, but in any case, a given torque makes sense relative to a given pivot point. And it's your job to state which pivot point that is. Now, often problems stated for you, but in general, you should get into the habit of telling us what your pivot point is. Okay? So, just to end this recap, let's write down the focus of today. Of course, the focus was to talk about torque and introduce that, but we also want to define a new equilibrium condition. Remember, we said earlier, this thing here, even though it satisfies the equilibrium condition F net y is 0, by the way, F net x is also 0. There's no force along x, so okay, F net x has to be 0 then. So I have both F net x is 0, F net y is 0, but this thing won't stay still. It has to go counterclockwise. So I do not have an equilibrium condition that I can work with if the object can rotate. So I need at least one new equation to say, well, okay, it doesn't go left, right, up, down, but also it doesn't rotate, please, because if it does, then it's not equilibrium. Well, then what we have to do is basically write a new equilibrium condition, which is that, well, we still don't want the thing to move left or right, so we still want F net x to be 0. We don't want it to move up or down, so we want F net y to be 0. And then torque net is going to have to be 0. And all three of these equations have to be true at the same time. And the first one says no motion left or right. The second one says no motion up or down. And the third one says no rotation. And if you have truly these three things at the same time, then you will have equilibrium. There's no option left for the object to move. It can't rotate, it can't move linearly, horizontally, or vertically, so okay, now it's stuck in place, it cannot move. And so that's our goal today, is to take this and apply it to a few classic problems so that you understand how it works. In the process, we're going to explain how we compute torque, how we draw extended free body diagrams, and the goal by the end of today is just to be good at computing torque, and then adding them up to 0 to get torque net. That's it. Okay. Just like we started with F net equals 0 at first. Then we'll move on to torque net equals I alpha. That's the equivalent of F net equals ma. Because, well, some things will rotate. They won't be in equilibrium. Okay, if they do rotate because of a torque, how fast do they go? Do they speed up? Do they slow down? What is it? Okay, well, kinematics play into that and so forth. So that'll be next week. And then we'll do energy, rolling without slipping, rotational kinetic energy, rolling kinetic energy, things like that. And hopefully by chopping it up like that, it makes more sense. It follows the same pattern that we followed previously. And also we spend more time on the important things in each individual part of this bigger chapter. All right, so let's take all this and have a look at this problem. Now this problem is so classic it isn't even funny. In fact, the next one is the same, the same idea. Both problems that we're going to do today are extremely classic. They're completely fair game, and in part they rely on a bit of initiative from you that nobody's going to really guide you, right? They're not going to say, oh, well, don't forget to do this. At best they'll say, oh, for example, find the force from the hinge. That's the best that's going to happen. But how you account for the hinge, that's on you. Okay, so we have a suspended beam, very straightforward. It is, you know, hinged against a wall. So if there were no cable, this thing would be free to simply swing down. And of course, a cable keeps it in place, keeps it horizontal. And we know the mass of the beam, we know the length, and the angle theta is 60 degrees. Okay, and we'd like to find the tension in the cable and the magnitude and direction of the force from the hinge. Okay. All right, so first things first, once you've done enough of these, it will be completely obvious that this is an equilibrium problem, but more generally, a problem where the object has a size and a shape that matter. And if anything, I mean, the fact that we give you the length kind of gives that away. So I need to find these forces. I need to find tension and the force from the hinge. And all I have is an object at rest that could rotate but doesn't. It also could move left, right, up, or down, but it doesn't. And so it's an equilibrium. And so that's really all I have to work with for now. And so let's just apply the equilibrium condition and see how we can solve for the forces. Now, before we do that, we need to draw an extended free body diagram of this beam. Okay? An extended free body diagram just means that you take the beam as is and you draw the forces where they are applied. So for instance, the tension force, remember, strings can only pull, will be applied at the right end of this beam. That's it. It's just applied right here. The weight force will be applied at the center of mass. By the way, this is why we learned about center of mass. The most important thing that you need to know about it is that for regular objects like beams, for example, and spheres and cylinders and things like that, the center of mass is located at the geometric center, which in this case, of course, is the middle of this beam. So somewhere roughly around here. Okay, maybe I don't get that exactly right, but to make sure that I make things obvious, I'll say L over 2 on either side, right? Even though my drawing might not be perfectly to scale. And if this is the center of mass, then the weight force is applied at the center of mass. Okay, that's the most important thing I needed to learn about center of mass, is to know that basically it's the point where if you apply the whole weight of the object, you get the same behavior as if you said, well, the weight is really distributed everywhere along this beam. Okay, so the center of mass is kind of a useful little point in that way. Okay, by the way, this is a 90-degree angle, so there's that. And then, well, we have to draw the forces where they're applied. And then that raises the question of the force from the hinge. Okay. Now, there is no formula for the force from a hinge. I've never seen it in lecture. It's not boxed somewhere in the book or in my notes. And in general, I do not know what a hinge does. I mean, I know that it allows rotation, just like it does on a door. But as far as exerting a force on the object that it's connected to, I don't know what a hinge does. Maybe it exerts a force like this, maybe like this, maybe like that. Kind of no clue. So what you typically do when you have a hinge is, rather than try to guess, because how would you know, just say, you know what, I am going to guess, but I'm not going to try to get the magnitude and direction right. I'm just going to say, you know what, I'll include an x component and a y component. And upon solving, once I know what the x component is and what the y component is, I can always get magnitude and direction. I know how to do that from components of a force. So that's what you do. You draw f of x and f sub x and f sub y, rather, and you solve. And you write the equilibrium condition. Okay, well, if I'm going to write the equilibrium condition, maybe I should just be completely clear as to what I mean by x, y, and what I choose for positive rotation. Now, it's not really going to matter here because there is actually no rotation. Torque net will be 0. So whether you choose counterclockwise or clockwise, doesn't matter. It adds up to 0 anyway. But let's say, just because it's the most common, that we choose counterclockwise as positive. Okay. So Then I'm going to write the equilibrium condition. The equilibrium condition states that f net x is 0, f net y is 0, and torque net is 0. All three at the same time. Okay, now the first two, easy peasy. We've done this a million times, okay? What's the net force along x? Well, okay, well, so it's f sub x minus, well, t cosine theta, because I want the adjacent component relative to theta and t. So that's going to be 0. In the y direction, I get t sine theta, that's the y component of tension, minus mg is equal to 0. That's easy. What's torque net? Well, torque net, kind of like work net in a way. Of course, you could say it's kind of like F net, but it's kind of like work net in the sense that if you remember when we went through work net, I said draw your free body diagram to show all the forces, and then if there's 4 forces acting on the object, there's 4 terms in work net. Well, it's the same thing here. You draw your free body diagram, and if there are 4 forces acting on this beam, then there are 4 torques that I need to evaluate. Okay. Now I'm going to say, well, it's the torque, therefore, of F sub x plus the torque of F sub y plus the torque of mg plus the torque of t. That all adds up to 0. Now I write plus between all of them because what I'm about to do now is go through each one and decide whether it's positive or negative. Okay. So let me take this with me down here so that we can refer to it without scrolling up and down. All right. And then let's figure out these torques. Okay, well remember, torque, well, I am going to scroll up. Torque is RF sine theta, right? And R is the distance between the pivot point and where the force is applied. So that means 2 things. First of all, it means that we have to choose a pivot point. So let's go here and choose a pivot point. But let's keep in mind that if we choose a pivot point where forces are applied, for instance, if I choose my pivot point here, then now the distance between my pivot point and the tension force is 0. So the torque due to tension is 0 relative to that pivot point. If I choose this pivot point, well, now the distance between my pivot point and mg is 0, so torque of mg will be 0. Torque of t won't be 0 anymore, but torque of mg will be. And so you see where this is going, where if I choose this as my pivot, well, there's no distance between that pivot and fx. There's also no distance between that pivot and fy. So the torque due to fy is 0, the torque due to fx is 0. Now that's kind of nice, it knocks out 2 torques. Plus it's torques of forces, I don't even know what the forces are, so maybe I don't want to compute torque of fx, that doesn't sound great. So then what you could say, well, which one do you choose? Which pivot do you choose? And the answer is it doesn't matter. Pick one, it doesn't even matter. Mathematically, you can pick any point as your pivot. You could even pick this point. It's a pretty dumb point to pick, but it'll work. Okay, the problem that you're going to run into, though, is that now you need to know the distance between this point and all these forces, and fuck that, that's hard. I don't know what that distance is, let alone the angle. I'm not doing it. But mathematically, that's a valid point to pick. So you can pick your pivot point to be anywhere mathematically. What we tend to do, though, is to pick a pivot point where there's a lot of forces, because then we don't have to worry about the torques from those forces. So you could pick this point, or this point. Those are probably your 3 most likely contenders. And there's a case to be made for any one of them. It doesn't really matter which one you pick. I'm going to pick this one because I want to knock out 2 torques from torque net. I want to get rid of torque of fx and torque of fy. But what you should do is then redo this problem and choose this point as your pivot. And your intermediate steps are going to look different from mine, but you and I are going to get the same answer in the end, and that's a great little exercise to practice this stuff. Okay, so let's say that I'm choosing my pivot right here. This is my pivot. That means that torque of Fx will be 0 and torque of Fy will be 0. Because any force located at the pivot creates no torque about that pivot. There's no distance between the pivot and the force, so no torque. So I only have to figure out torque of mg and torque of tension. Okay. All right. Well, let's start with torque of mg. First of all, is it positive or negative? Now, when I look at torque of mg, I forget all the other forces. I imagine they do not exist. I only contemplate mg. Now, hopefully, you would agree that if we pull this beam along mg, forget everything else, there's no tension, no fx, no fy, the tendency will be for this beam to rotate clockwise. Okay, if there's no cable, mg pulls this thing clockwise. Now clockwise, that's negative, because I said counterclockwise is positive. So this is minus, now the distance between the pivot and the force is L over 2. The force is mg. Sine of the angle between L over 2 and mg, and that's 90 degrees, which is convenient because sine of 90 is 1. So this is minus mg L over 2. What about the torque due to tension? Okay. Well, again, I forget all the other forces but tension. No mg, no fx, no fy. I imagine that there's only tension. If tension pulls in this direction on the rod, hopefully we agree that the rod would want to rotate counterclockwise. That means that the torque created by T is positive because counterclockwise is positive. It's going to be the distance between the pivot and the force, that is L, times the force, that is T. Sine of the angle between L and T, that's theta. All right. Those are the individual torques. Net torque is the sum of the two. And like I said, I always write plus, plus, plus. I just add them up. And then one by one, I figure out which one's positive, which one's negative. You could do it in one fell swoop, right? If you get good enough at torque and you get enough practice, you'll see that you'll do this step and this step at the same time. But for now, you know, we're still learning, so let's not rush too quickly through this. Okay. So now I have this, and, well, let me just sub in torque of mg and torque of t. So this is going to be minus mg L over 2 plus L, what am I doing? Duh. Minus mg L over 2, that's better, plus L T sine theta. And that's got to be 0. All right, so now I have 3 equations. 4, in fact, 3 unknowns. I don't know fx. Oh, I forgot fy, didn't I? That's embarrassing. And nobody caught me. Yikes. Well, I will never let a good mistake go to waste. I will point out that I'm a dum-dum for making that mistake, but it's a common mistake to forget fx or fy. But yikes, my bad. Sorry, I went a little too quickly there when I wrote f net y. So let me correct that. So yeah, there we go. Plus fy. Okay. All right, so I have Well, they're saying 3 equations for 3 unknowns, fx, fy, and t. Those are my 3 unknowns. Now, the easiest thing to do to solve for tension is, first of all, it only shows up in the 3rd equation, but it turns out it's the easiest thing to do because it's the only unknown in the 3rd equation. So L goes away, and I find that T is equal to mg divided by 2 sine theta. Okay, and that's 100 times 9.8 divided by 2 sine of, I think, 60 if I recall. And let me compute that real quick because, okay, so there you go. 2 times sine of 60. And we're in degrees, and that's 565.8 Newton. All right, so that's tension. And that's the first question, find tension. Then it's find the force in magnitude and direction from the hinge, which means I have to find fx and fy. Okay? So, to find fx and fy, now that I know t, it's very straightforward. I can just use these 2 equations and plug in t. Okay, so fx is going to be t cosine of theta. Well, that's going to be mg cosine theta over 2 sine theta. Of course, at this point, we know t anyway, so you could just plug t in, but just to make sure we do everything with variables at first, then we're going to get cosine of 60 in there. That's going to change the answer to 282.9 Newton. All right. So that's for the x component of the force from the hinge. And then for the y component, Fy is going to be mg minus t sine theta. Okay, so that's going to be mg minus, now t sine theta, that's mg over 2 sine theta. That's just t times sine theta. Okay, so sine theta goes away. Mg minus mg over 2 is just mg over 2, which is 100 times 9.8 divided by 2. That ought to be 490 Newton. All right, so that is how I find the components fx and fy. Not quite what the problem asks me to find. Yeah, I have to say that the magnitude of f hinge is going to be equal to, this is the Pythagorean theorem, f hinge is equal to square root of fx squared plus fy squared. Okay, so that's the square root of 282.9 squared plus 490 squared. Well, that's going to be square root of 282.9 squared plus 490 squared. And that's about 565.8 Newton. All right, so that's the magnitude of the force from the hinge. What's the direction? Well, let's find out. Okay, I know the x component, right? Don't draw fx, and I know how big it is. I know the y component, Fy, and force of hinge is going to be like this. It's going to be Fh, or F hinge. And it's going to be at some angle, I'll call it beta, from the horizontal or the vertical, it's up to you. But if you draw it relative to the horizontal, then you're going to get this kind of triangle. It's going to be Fy, and this is going to be Fx. And so tan of beta is going to be Fy over Fx. It's opposite over adjacent. Now, we know what these are, and so we can just compute it, or we could just plug in variables first. I'm going to plug in variables. So I'm going to say that this is Fy is mg over 2, Fx is mg cosine theta over 2 sine theta. All right, mg over 2 goes away. I get sine over cosine. That's tan theta. Okay, tan beta equals tan theta. That means beta is theta is 60. Okay. All right. Now, I did this on purpose because you're like, oh no, that makes sense because, you know, if this is theta, then probably this is going to be theta 2. You know, it's like, well, ish. It was a fluke. Complete luck that beta was equal to theta. Okay, so in general, what I want you to keep in mind is that whatever the force from the hinge is, whatever beta is, there's no reason for beta to be equal to theta. There is also no reason for beta to be 0, and therefore for the force from the hinge to be horizontal. Now, that's a very tempting thing sometimes, especially if the rod is not horizontal to begin with. Right? So in some problems you'll have the wall like this. This will be the rod, and then this is tension, right, keeping it in place. And then when the force from the hinge is computed and the direction is computed, somehow we want the force from the hinge to be along the rod. And that's not true. There's no reason for that to be the case. It could be, if it is, it's a fluke, it's just luck, but there's no reason why that should be the case. So my point here is just find the components, and whatever you get for beta, that's what you get. That's what the problem works out to be. If it turns out to be theta, it's luck, fine, I know that theta is 60, so that's my answer. If it turns out to be completely different, like 17.2 degrees, well then it's 17.2 degrees. But you compute it from the components. Okay. So it's your job to introduce the components. As you can tell from the equations that we had, it's a lot easier with components. Right? I just throw fx and fy in there. I have no idea what they are, but it's okay. I now have 3 equations, so I get to solve for fx, fy, and t. Right? I get to solve for up to 3 unknowns. You tell me what you want me to solve for. But if you're going to throw the force from the hinge in the mix, I'm going to throw the components in the mix because it's going to make my life a lot easier to solve for them, right? Because they show up, and they show up in separate equations because, of course, one's along x, one's along y. Okay. So, well, hopefully that makes sense. Hopefully that wasn't too quick. This is a classic problem. I would recommend you do it again, right? Just check that you get the same answer I got. And then do it another time. Instead of choosing your pivot here, choose it either here or at the right end. Choose a different point to be your pivot. And it won't change F net x and F net y. It will change the torque net equation. But at the very end, once you solve, you'll get the same answer that I did. Right? So it doesn't matter which pivot point you choose. Just pick one, stick with it, and you'll get to the final answer. All right. So now that we're warmed up, let's do another. This is also extremely classic problem. Matter of fact, you've probably already seen it in discussion if you've made it to statics at this point. So we have a ladder, mass m, length L, and it's at an angle theta with respect to the ground against a frictionless wall. So I'm going to write mu is equal to 0 for the wall. And there's a coefficient of static friction between the ladder and the floor, which is 0.7. Okay, which is not going to matter, in fact, because I only have variables, so you might as well just call it mu s. But the point is, you do need friction between the ladder and the ground. If there is no friction between the ladder and the ground, the ladder will never stay put against the wall. However, friction from the wall, it's a nice to have if you have it, but it's not required for the ladder to stay in place. Now, that might not be obvious just by looking at it, so we are going to draw the extended free body diagram, and we're going to see that even without friction from the wall, I can get F net x to be 0, F net y to be 0, and then torque to be 0. Okay, and we want to calculate the minimum value of the angle theta at which the ladder will not slip. Okay, so hopefully that makes sense, that if you ever have used a ladder, or if you're contemplating using a ladder, you would want to probably get it to be, as steep as possible against the wall. Not too steep, that's the problem, but, more like this than like this. Okay, first of all, like this is completely idiotic. There's no point if the point of the ladder is to get to a meaningful height. Plus, this thing is begging to fall, right? This is going to slip out, and then you're going to fall. So, seems to make sense that the smaller you make theta, the more likely you are to see this contact point with the ground slip out to the right. So we're going to try to find theta. Okay, well, we already know xy and counterclockwise positive, that's given. And in fact, most problems will give that to you like that. We all grade the same copy of your exam, it's always nice. But if it's not there, you would draw it, and if it is, then you just roll with it. And the next step after x, y, and counterclockwise is the free body diagram. So I'm going to draw the extended free body diagram of this thing. And what it means is I'm going to draw the forces where they are applied. Okay, so the easiest one to draw is the weight force. Okay, this is going to be mg. It's going to be at the center of the ladder. This is L over 2. This is L over 2. Then the contact point with the ground, well, that's pretty straightforward. It's going to be a normal N1 because the ground pushes up on the ladder. And then similarly, in fact, there's going to be a normal N2 from the wall. Now that's not sufficient because in the y direction, these two can cancel, that's fine. But in the x direction, I have N2. And so N2 doesn't have anybody to cancel with, meaning that F net x is not going to be 0, and this ladder cannot remain at rest. Well, of course, that's because I forgot friction here, right? Now the question is, what is the direction of friction? Well, first of all, it's static friction because I don't want the ladder to slip. Second of all, I know that static friction points opposite the direction in which I would slip. So static friction is going to point to the left because if I slip out that way. That's convenient because it's going to then cancel with N2, ensuring that F net x is equal to 0 as well. So I don't need friction from the wall. Now if I do, I mean, cool, like it's going to point like this, but I probably should call that Fs2 then, but I don't need that. And here there's no friction, so I'm not going to draw it. But this is good enough to write the equilibrium condition. Okay, so what's the equilibrium condition? Well, I need to have F net x is 0, F net y is 0, and torque net is equal to 0 simultaneously. Okay, so we'll go a little bit faster here. We're going to write out F net x, say it equals 0, F net y, say it equals 0, and the torque. Okay, now F net x is going to be N2 minus Fs. That's going to be 0. F net y is going to be N1 minus mg. That's going to be 0. Torque net, well, I don't quite know yet, but I know that there's 4 forces, so there are 4 torques. So it's going to be torque of N1 plus torque of Fs plus torque of N2 plus torque of Mg. Okay. Now, by the way, just real quick while we're at it, if you look at this triangle here, that's a right triangle. That means that if this angle here is theta, this angle here is 90 minus theta. I just need that for later. Okay, so my net torque is all these 4 terms that add up to 0. Torque is computed with respect to a pivot. I need to tell the grader what my pivot is, because nobody said you have to pick this point as your pivot. It's up to me. Okay, so I could pick, again, any point will work mathematically, but the 3 best contenders are these 3 points here. Right? So either this guy, or this guy. Now, I remember that when a force is applied exactly at a pivot, then there's no distance between the pivot and the force. The torque that force creates is 0. So I could choose any one of these guys, but the choice that's going to knock out the most torques is this guy. Right? It's going to knock out the torque of N1 and the torque of N2. So I'm going to put my pivot down here. Okay? Which means that now torque of N1 is 0, torque of Fs is 0, and that's because N1 and Fs are applied at the pivot. Okay. So now I have the following system of equations. I have N2 minus Fs is equal to 0, N1 minus Mg is equal to 0, and then I have to find the torque of N2 and the torque of Mg. So let's come back up here so that we can do it next to the drawing. Torque of N2. So I forget all forces except N2. And if I look at my ladder, right, and I look at N2, hopefully I agree that N2 tries to pivot the ladder clockwise. Okay, and clockwise, that's negative. So the torque from N2 is minus. The distance between the pivot and N2 is the length L of the ladder. The force is, of course, N2. Sine of the angle between the ladder and N2, that's this angle here, that angle is theta. Right? These are alternate interior angles or whatever they're called. And so this is going to be sine theta. All right, so that's torque of N2. So I'll bring that down here. What about torque of Mg? Okay, well, let's find out. Torque of Mg is equal to, forget all the other forces except Mg. If Mg pulls down like this on the rod, hopefully you agree that the rod would want to pivot counterclockwise. Okay, I'm not saying it does, I'm saying that that's what it would want to do under the effect of Mg. So that would be a positive torque. The distance between the pivot and Mg is L over 2. The force is Mg. Sine of the angle between L over 2 and Mg, well, that's 90 minus theta. That's why I needed that guy. Okay, well, that's going to be Mg L over 2 cosine theta, because sine of 90 minus theta is cosine theta. Okay, so then plus this is equal to 0. And the length L of the ladder clears out. Okay. Now I'm looking for something very specific. I am looking for the smallest angle for which this thing does not slip. And this is starting to look like previous stuff with static friction, which is kind of a pain. Right? Static friction, I never know what it's equal to. It's equal to whatever it has to be for equilibrium to apply, but I want the smallest angle that I can have. So the smallest angle that I can have is going to be the angle for which the ladder is just on the verge of slipping.
with Fs equal to mu s times the normal. By the way, this normal or this normal should be n1. Hopefully we agree. n2 knows nothing about friction. There is no friction between the wall and the ladder. Okay, so Fs is the force that arises related to n1, so the max static friction force is mu s n1. Okay, and just as previously, we have to say this. We have to say for theta equal to theta min, the ladder is on the verge of slipping with Fs is equal to mu s n1. Okay, so now I have n2 is equal to Fs, which is mu s n1. n1 itself is equal to mg. And then I have n2 sine theta min plus mg over 2 cosine theta min is equal to 0. All right, so I can plug n1 into this, n2 into here, and so n2 is mu s n1, but really n1 is mg, so this is mu s mg sine theta min plus mg over 2 cosine theta min, and that's 0. Okay, mg goes away. If I ever have to solve for, I got a minus that I dropped here, didn't I? Minus, there we go. If I have to solve for theta min and I have sine and cosine in the same expression, one thing that I might want to try is to get tan. Okay, so I'm going to get mu s sine theta min is 1/2 cosine theta min, and that's not equal to 0, that's just already rearranged. And so, okay, so then sine theta min divided by cosine theta min is equal to 1 over 2 mu s. All right, so tan theta min is 1 over 2 mu s. All right, so theta min is inverse tan or arctan, same thing, 1 over 2 mu s. Turns out, because we know mu s, we can actually compute this thing. So this is 1 over 2 times 0.7, and that's going to be equal to about 35.53 degrees. Okay, so actually quite remarkable. It's independent of the mass and the length of the ladder. It is only a function of the coefficient of friction between the ground and the ladder. So, zooming out real quick, another classic problem. And again, like I said, you will recognize these. I mean, once you see a few, they kind of just jump out at you and you're like, oh, that's a torque problem. By the way, it's at rest, so it's a torque net equals 0 problem. Okay, so the ladder against the wall is a classic. The one we did before is also a classic, the horizontal beam. In the same family, you have the drawbridge, right, from the castle or whatever. All of these solve the same way. It's free body diagram, extended free body diagram. So you have to show the forces where they're applied on the object. F net is 0 along x and y, torque net is 0, all three at the same time. Make sure you indicate what your pivot is, you write your equations, and you solve. And so if you really want to practice these two, you can
redo them, kind of alongside me with the way that I solved with my pivots, then go redo them with a different pivot and convince yourself that it ties. It's a great exercise to do. I'm not saying do it every time, just a couple times at first when we first learn about this, just to cement into your brain that it doesn't matter what you choose as the pivot, it just matters that your equations are set up consistently with respect to that pivot. You solve, you'll get the same answer. Just the intermediate steps are going to look a little bit different, but at the end you get the same answer. So that was the goal of today, to just discuss the fact that we are now dealing with objects that have a shape and a size that matter. More on that next week when we talk about moment of inertia. And we needed a new equilibrium condition because there's a new type of motion that we need to account for, which is rotation, which either doesn't occur, that was this week, or in fact does occur, in which case, if you think of a propeller, is it speeding up, is it slowing down? How is that related to torque? And so that's the next part, which mirrors what we did before, where after F net equals 0, we said, well, okay, F net can also be ma, and if F net is ma, and that explains linear motion, then torque net equals I alpha is going to explain rotational motion. We're going to have to talk about, well, not torque, because we know what it is, but we are going to talk about I and alpha, the moment of inertia I, and alpha, the angular acceleration, and tie that back to kinematics. Because we're going to need, of course, new kinematic equations, because it's a new type of motion. Now, they look so similar to the previous ones that it's not a big leap, right? But we still have to introduce them and talk about that. So this is part 1 of 3. Next week we'll do part 2, which is dynamics, or Newton's second law for rotational motion, if you want to call it that. And then the week following we'll do rolling without slipping, kinetic energy, and so forth. And again, I know it's not typically the order in which it is taught. I don't, if someone can explain to me why teaching it the way it is taught makes sense, I'm happy to listen, but again, I think this makes more sense because it's the same progression that we did for forces through Newton's laws and then into energy, as opposed to just doing it in a different order here. And again, my goal is step by step. First we learn about torque, then we can tack on I alpha, and then we can move on to energy altogether. And hopefully by doing that, it's 3 bite-sized pieces as opposed to one big kind of sludge of stuff that gets thrown at you almost all at the same time. Anyway, thanks for watching, as always, appreciate it. Midterm 2 is, okay, it's not coming up quite yet, but it will come up quick, so don't let it surprise you, because at this point, as you know, after midterm 1, everything goes crazy. So physics 2 is no exception. Midterm 2 tends to be, students tend to like midterm 2 less than midterm 1, let's put it that way. And I think a big part of it is torque, because it's very new. It's usually the last thing you did just before the midterm, unless you did a little bit of fluids, but it's the most recent thing you've done, so you don't have a lot of, of time to kind of get comfortable with it and feel good about it. And, it's just, if you've taken AP Physics before, this is where, the wheels might come off the cart a little bit, where you might have had some kind of advantage the first few weeks of class. Here, depending on how far you went into AP Physics and how well it was done in high school, the advantage might not be so clear. So, make sure you spend time on torque. It's worth it, and because it's going to be a good chunk of the exam anyway, and it's probably going to be on the final 2. To be honest, it's almost irresistible. I mean, torque is such a great chapter. There's so much that we can test you on that it's not surprising if it's both on the midterm and on the final. Anyway, hope you have a great rest of your week. I will see you next week for part 2. Thanks as always for watching, and for those of you who contact me, I'll get back to you by end of day. It's been a busy beginning of the week, but I'll get back to you. And on that note, if you need to reach out, feel free to. Always happy to clarify or answer your questions. All right, take care. Have a good one.